Okay, so let's think about it. Clearly, since it's a negative charge, it's repelled by the negative side and drawn toward the positive side, which is where there's higher voltage, right? So a negative charge wants to go from low voltage to high voltage. Therefore, as it does so, the charge will gain kinetic energy. And you don't have to push it. It doesn't take any work. Oops, most of you went for that one. It takes work to move the charge. Now, I can kind of understand why you might go for that. You could think, well, it's the electric field doing work on the charge. And so B is maybe kind of true, but A is really the true one. It doesn't take, the charge, you could actually extract energy from the charge moving in this field, right? You could, if you had an object that was charged up, it would gain, it could do work on, the field could do work on it. Okay, so let's think about the electric field due to a point charge again. And that's, the field lines radiate out in all directions, not just in the 2 dimensions of the screen, but really in 3 dimensions. So you should imagine the field lines as pointing in all directions. Now we'd like to talk about how does the electric potential work. Well, contours of constant electric potential are drawn here. In the slice, in the 2-dimensional slice of the screen, they're circles. But in fact, they're really spheres. And this sphere could have V, electric potential voltage equals 1, 2, 3 volts. As you get closer and closer to the charge, the electric potential gets larger and larger. That's one way to visualize the electric potential. The way we would normally do it in physics courses is to draw just a graph of the potential, which we know is kq divided by r. So if q is greater than 0, you have a curve, which is a hyperbola that looks like this. It's a 1 over r dependence of the electric potential on distance. If you have a negative charge, the potential is also 0 out in infinity, but you have a hyperbola that goes down to negative infinity as you get arbitrarily close to the negative charge. Now, this is a lot more abstract way to represent this. And it doesn't necessarily bring up in your mind when you look at a graph like this, the sort of 3-dimensional picture of how it looks. So we can also draw a picture of the electric potential like so. Here we have a positive charge, and this sheet represents, the height of the sheet represents the voltage at any point as you get closer and closer to the charge. Well, the closer you get, the bigger it gets. It actually is going to infinity. And likewise, if you have a negative charge, a positive charge would feel negative, be attracted to it and would tend to roll toward the negative charge. And that's sort of depicted by the fact that this surface is going down to negative infinity here. Away from the charge, the potential is nearly 0. That's what this sort of represents. Now, it's very difficult to represent that in 3 dimensions, right? Maybe we could do it with color or something like that. You could have a picture of a positive charge, and the closer you get to that positive charge, the more brightly it's glowing or something like that. That might be a way to think about the electric potential. But suffice it to say that electric potential is just something that goes to either positive or negative infinity as you get to the point charge with a 1 over r dependence. So let's do another clicker question. If the potential from positive charge is 1 volt at a distance of 2 meters, at what distance will it be 4 volts? How close do you have to get to it?